The modern search for extraterrestrial intelligence really starts with a landmark paper by Philip Morrison and Giuseppe Cocconi in 1959. Frank Drake famously started the first modern SETI experiment in 1960 as Project Ozma, and a number of efforts since have been made by scientists around the globe and are ongoing to try to listen in on technological signals of alien origin. If any one of these detects an unambiguous technological signal not made by us, then this will be among the greatest discoveries of the entirety of human history. And there have been candidate signals, perhaps most famously the Wow signal of 1977, but nothing conclusive yet. But SETI is particularly fascinating in that it could change in a very short period of time, and an unambiguous signal could be picked up one day and there it is. We are not alone. But the search is only just starting. Space is unbelievably vast, and searching as much of it as is viable is very incomplete. We have sampled less than a pond's worth of water in an entire vast ocean, and we have a long way to go in a pursuit that could get lucky at any time. My guest today is a long-standing and important figure within SETI, who continues to search, along with many other scientists, for the elusive signal that, when caught, will change the world.
You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Jill Tarter. Jill Tarter received her Bachelor of Engineering Physics degree with distinction from Cornell University and her Master's degree and a PhD in Astronomy from the University of California, Berkeley. She served as project scientist for NASA's SETI program, the High Resolution Microwave Survey, and has conducted numerous observational programs at radio observatories worldwide. Tarter's work has brought her wide recognition in the scientific community, including the Lifetime Achievement Award from Women in Aerospace and 2 Public Service Medals from NASA. Tarter is deeply involved in the education of future citizens and scientists. In addition to her scientific leadership at NASA and SETI Institute, Tarter was the principal investigator for 2 curriculum development projects funded by NSF, NASA, and others. Many people are now familiar with her work as portrayed by Jodie Foster in the movie Contact.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice. Dr. Jill Tarter, welcome to the program.
Thank you, John. Pleasure to be here.
Doctor, I have been a SETI enthusiast for probably 35 years now, since I was a teenager, maybe even a little bit before. And you've been around the whole time. You have been in SETI maybe longer than anyone. Now, what originally piqued your interest here? At what point did you look up at the sky and say, I wonder if there's someone out there?
Well, for me, that was when I was a very young child, walking along the beaches of the Florida Keys, the Gulf Keys. And my father was explaining the constellations to me. And it was back then, those keys were incredibly dark. They were uninhabited, mostly, no street lights, nothing like that. So the sky was beautiful. And I just wondered if somewhere on a planet around one of those stars, a creature would also be walking along the beach with its parent and seeing the sun, our star, in its sky.
It's kind of an interesting thought that maybe one commonality that we would have with alien life is beaches. Because if liquid water or some solvent of life, maybe ammonia or something like that, is obviously key to biochemistry, so they would probably have beaches, right?
Could well be, yes.
Now, within SETI is hard. And there's no question that you're looking for a needle in a haystack in a universe that emits enormous amounts of radio naturally. So what is it that you look for? What characteristic is it that you look for in a signal to differentiate it from, say, just some event in the cosmos? Is it narrowband signals, or is that also not a very good indicator?
No, in the radio, we use frequency compression, the fact that it's a very narrow band feature. And in the optical, we look for time compression. We look for a very bright pulse that is also perhaps monochromatic because it's a laser. So the frequency compression in the radio is a good bet, because when nature emits, it does so on the basis of multiple atoms or molecules, and they have relative motions to one another. And so even though a particular atom or molecule might emit at a particular precise single frequency, because the ensemble of the emitters is necessary to get enough intensity to have an observable radio feature, though that will be spread out in frequency space. But with technology, you can get something to radiate at a precise single frequency. That doesn't look like nature at all.
So in other words, say you're looking near the hydrogen line at 1420 megahertz, you'll see hydrogen gas clouds, but it sort of smears across the spectrum slightly because of the hydrogen atoms moving.
Right.
If you have an intentional signal being sent from a transmitter, it doesn't do that.
That's correct. Correct.
And that's smart, because it doesn't waste energy. So you're not broadband, you're not leaking energy that way. You're being very precise, and that screams technology.
And by the way, perhaps in their civilization, they, like we do here on Earth, protect the frequencies surrounding that hydrogen line and don't allow transmitters because they want to be able to see the natural sky.
Now, the hydrogen line, as far as natural radio astronomy goes, what is special about it that we study it just on a survey basis? What is special about that area of the spectrum?
Well, hydrogen is the most abundant element in the universe, and it aggregates into clouds. And by studying the line, we can actually study the motions of those clouds relative to one another. So we can look at, for example, an external galaxy and look at how the emission around the hydrogen line from a region of the galaxy has been either redshifted or blue shifted relative to its laboratory value. We can then see the rotation of the gas in the galaxy. We can, in fact, use that to help us measure the mass of the galaxy as you look out towards the edges and see how rapidly these hydrogen clouds are moving.
Now, it was also, the point was made long ago, I guess, by Morrison and Cocconi, that alien scientists would also know this, hydrogen obviously being the most abundant element in the universe. And they had the idea that, well, maybe that's the ideal place on the dial to put a signal or near it. So when you look at the sky with a radio telescope looking for a SETI signal, so how many channels do you use? You know, how many channels are you monitoring? And do you sort of center on that line, or do you look at others?
Well, it depends on when you're asking the question, because the technology has changed enormously over the decades that we've been doing this. So starting out, we had 100 channels, PAR autocorrelator. Today, there are billions of channels that we can observe simultaneously because of the advances of computing and instrumentation. And we prefer not to play this magic frequency game that is, it might be the hydrogen line or pi times the hydrogen line, or OH, because that's the other piece of water along with hydrogen. So we just try and observe all frequencies within what we call the terrestrial microwave window, which runs from 1 billion hertz up to 10 billion hertz. So 1 to 10 gigahertz. Frequencies lower than about a gigahertz, you begin to pick up excess noise due to synchrotron radiation. That is, electrons spiraling around the magnetic fields of the Milky Way galaxy. And it gets stronger as you go to lower frequencies. Much above 10 gigahertz, and you start to pick up emission from water vapor and oxygen in the Earth's atmosphere. So at least from the ground, there is this quiet terrestrial microwave window. And that's the region of frequency space that we've been trying to explore. But as I said, it's 10 billion channels.
Now, within that, are there hopeless frequencies where humans have just emit so much radiation that you just can't even look there?
Yes, absolutely. There are places where our own technology just totally swamps the natural signature. We generally call them bad bands, but it is interference from our own technology. And it's getting worse over time. We're losing more of the spectrum. So that has encouraged people to think about putting a telescope in the one location that never has the Earth in its sky. And that would be on the far side of the moon, which is certainly going to be an expensive proposition. And even though we would not see the interference from the Earth, NASA and ESA and spacefaring nations are beginning to think about building what they call a gateway station above the far side of the moon for further exploration and communications back to Earth from the far side. So, although it's quiet now, it may not remain quiet forever.
In these frequencies that we use very heavily, are there advantages to those frequencies that might be universal? In other words, could it be that the alien signals are at the same frequencies that we use heavily for some reason, or is that just arbitrary? I mean, is it just that we chose those frequencies just because, or are there advantages in those noisy frequencies to actually broadcast at them?
We've not been able to make any kind of compelling argument about universality. Certainly, we believe that the elemental composition of the universe is the same everywhere. But we've not been able, as I said, to definitively come up with some special frequencies. People have made lots of arguments about special frequencies, but none of them, at least to me, are compelling. So I think we need to search throughout. And when we get above the Earth's atmosphere, I think we also ought to be going up higher in frequency.
Why is that?
Well, because if you get above the atmosphere, then you lose the noise from the water vapor and oxygen emissions in the atmosphere. And so now you have a clearer look into the cosmos at higher frequencies.
I see. So you remove the opaqueness of the atmosphere, and therefore you've got a much, much broader palette to look at the spectrum. In fact, all of it really, right?
Yes, I think you're still going to be blocked at the low end by synchrotron emission from the galaxy. But yes, once you get above the Earth's atmosphere, the higher frequencies have become quieter and accessible.
The beauty about the synchrotron radiation, though, is that's something that the aliens could predict. So if they want to send out a signal, they would know about that and not broadcast there, presumably.
Well, it's a broadband phenomenon. So it starts to be loud at around the gigahertz. And then as you go down in frequency, it gets stronger and stronger. It is kind of a continuum emission feature rather than a line.
Now, the argument is often made, and I mean, presumably you could eavesdrop on an alien civilization's internal communications or something like that. But the real option here is if the aliens have noticed that Earth is screaming biosignatures and has for billions of years, and they decide, well, let's point a transmission directly at that little planet and make ourselves known, a beacon. And in that situation, people have made the argument that aliens wouldn't do that. We an advanced alien civilization, we'd be like ants to them, and they wouldn't pay any attention to us. And that argument is often made. But I disagree with it in that I think that we have scientists on this planet that study ants. And we have entire television shows, National Geographic and all that, talking about ants. And we're very interested in ants. And I would think that any life in the universe would be of interest to alien scientists. Do you agree or disagree?
No, I agree with you on that, John. I think one of the questions that an advanced technology civilization might be trying to answer is, what is the variety of life possible in the cosmos? How can things be different elsewhere? Is there only one way to make biology? And maybe on this planet, we will answer that question in the laboratory with synthetic biology, but we could also answer it by finding examples of life unlike the life that we have here on Earth, somewhere else. So we're going to be looking for life on Mars and Europa and Enceladus in all kinds of different ways. And if we were to find life in any of those places, particularly Mars, then there is definitely a second question to be asked, which is it related to life on Earth? Or is it in fact actual second genesis, another way of making biology? And so I think that's exciting. And I think that curious technological civilizations elsewhere would like to know the diversity and complexity of life in the cosmos.
Well, naturally, one would say that alien scientists would want as complete a picture of the universe as they could possibly get. That's the point. Figure it out. Therefore, studying us becomes part of that data set anyway. So why wouldn't they be sending, if they could, sending anthropologists, human studiers, or, even alien scientists that want to study Earth's ants? Why wouldn't they send a host of scientists if they want a complete picture of the universe at large?
Assuming that interstellar travel by large macroscopic entities is possible.
Assuming, of course, we don't know that. And that may be so expensive that it's all telescopes, which doesn't that make it a little bit harder to spot, that if civilizations never really see the energy expense and just the general expense to cross interstellar space, and then everybody's stay-at-home civilizations, doesn't that make SETI harder?
It does. On the other hand, what we've been doing more recently is trying to expand our horizons in terms of what might constitute not a biosignature, but a technosignature. How might advanced technologies elsewhere be consuming energy to do work of various kinds that might have discernible ramifications, particularly with this huge new suite of large optical and infrared telescopes that will be coming on the air this decade. So what is it that they might be doing that we could remotely observe and infer that was the result of a technology? There are a couple of interesting ideas along this line. If we have a geosynchronous belt, right, which we use for broadcasting, and if they on another planet went into this in a really big way and created what's often called a Clark belt of objects that transmit. And because to be geosynchronous, the distance has to be the same. You could only essentially go, to put more stuff up there, you can go up and down the plane. And that might produce a kind of a ring that would be visible with a sufficiently sensitive telescope. So maybe we might detect that. Another idea that's been suggested, and again would be an offshoot of astronomical observing programs, would be that an advanced technology which lived in the vicinity of a Cepheid variable star, a star that expands and gets brighter and then contracts and gets dimmer and then expands again and contracts with a fairly constant period. If they were able to orbit some large energy source around such a Cepheid variable, and they would watch the star expand and contract, and it wouldn't normally be ready to expand again, but if they inputted a large source of energy, they could make the atmosphere of this Cepheid expand prematurely. And then what you've actually done is created a Morse code that could be seen anywhere across the galaxy, actually all the way out to all the way through the local group of galaxies. And you'll have the natural period, and then you'll have a short period. So you'll have a dot and a dash, and you could communicate over vast distances, not having to pick out your target because you created an isotropic radiator. Good science fiction. Don't know whether anyone could ever do that, but it's an idea. So we've had students looking at the 100-year history of the Association of Variable Star Observers, looking at the history records of Cepheids and other pulsing sources to see if we could find this extremely interesting pattern. You know, the most often discussed technosignature would be a Dyson sphere or a Dyson swarm around a star to capture all the energy that it emits for the technological civilization that's on a planet in that system. That can have observable consequences. We're thinking about various things that we might be able to observe commensally with these new beautiful telescopes. And commensal just means eating out of the same bowl. So it means it's not parasitic. You actually find a way to make copies of the data. We can do that very easily in the radio now, and it's getting easier in the optical. So that one cohort of scientists can be doing their astronomical observing, while another cohort could be analyzing the same data in different ways, looking for technosignatures. In fact, there's a project at the SETI Institute that's being run by Andrew Simeon. It's called Cosmic, and they will be going to the VLA, the Very Large Array, and arranging to make a parallel data stream out of each of those 27 antennas. And that data stream can be analyzed for SETI signals while the astronomers are doing whatever they're doing with the VLA. So you can, in theory, be on the air 24/7 with a very powerful telescope.
Piggybacking, and it doesn't cost a thing because the telescope's already taking the data, but that creates a mountain of data. So how do you sift through all of that data?
Well, you build a lot of algorithms and you use fast computers so that you can keep up in near real time. And then you inevitably end up using machine learning to help you sift through this great data stream. But I'm excited about that project. It's something that I wanted to do 30 years ago, thinking about doing it in software as the astronomers were making their radio maps. I worked with a gentleman, Barry Clark, at the VLA, and it was just totally out of the question because we couldn't handle the data rates that you'd need. So, but now, new technologies, GPUs, FPGAs, all this kind of thing, allows us to compute fast enough so that this becomes a possibility.
Now, this is an odd question. So when you first started in SETI, these were the days where you had like the big ear telescope with a receiver that had 10 channels, and now we have billions. Did you back then foresee a day that SETI would be this advanced as we are today?
Well, I can't say that I could paint a roadmap, but in fact, that was one of the things that kept me intrigued and working on SETI was the fact that we could see that today we could do our searching better than we could 2 weeks ago. I mean, we could see the improvement in compute power. And so we didn't get totally overwhelmed by how large the search was in comparison to what we could do, because we knew that in the future we could do more. And, Moore's Law has been around for a long time, and we certainly on board.
That experiment, the Big Ear, yielded, to my knowledge, the best candidate signal yet. And unfortunately, it was very early in the game, 1977, and the WOW signal. What's your opinion of the WOW signal? Do you think that is maybe that was it, or maybe it just was interference?
If I had been running that project, you would never have heard of the WOW signal, because it did not manage to successfully navigate the protocols that were set for deciding whether it was an interesting extraterrestrial signal. So the WOW signal, the Ohio State Telescope was built with 2 receivers, and it's basically a transit instrument. That is, you can't pick up that huge football field and move it around. So you set a declination strip on the sky by moving one movable piece of the telescope, and then you let the sky go overhead, and you see what you find. And a real signal coming from a distance and traveling at sidereal rate, the rate at which the sky appears to move, would have first been picked up in the east receiver, left that receiver, and then be picked up in the west receiver, and left that receiver. The signal was only seen in one of the 2 receivers, and they had no way of knowing which. And so it did not rise above the threshold for detection of an extraterrestrial signal that they had set. And I think that I'm maybe just being too stubborn and dogmatic here, but I think if you set up a series of ground rules for what's going to constitute a signal that you're interested in, potential candidate, then you can't change the rules after you start. So the WOW signal would not have passed the test, and I would have discarded it.
But by virtue of it being so early, 1977, it maybe it's more interesting because of that. In other words, a lack of signals, other signals to compare it to. So maybe we have a different bar now after decades more work in SETI, right?
Well, I would argue, John, that they had set this protocol when they began their observing. And it was a protocol that they expected could be fulfilled. And this signal, was very strong, but it did not really fulfill the definition that required it to be a point source moving on the sky at sidereal rate. So it's just a different opinion. I mean, I'm probably the only one that says that, as everybody else says, oh, the WOW signal, maybe that was it. And I think the thing that annoys me is that subsequently astronomers have spent, including the team at the Allen Telescope Array, have spent a great deal of telescope time trying to follow up and see if they can acquire that signal. And so it caused a lot of perhaps wasted telescope time.
Now, do you find, or do you see signals like that? In other words, ones that you discard and say, yes, this is not. Do you see those
yes.
today?
Yeah, absolutely. As we do our signal processing in near real time, which means that we had a 3-step pipeline, and you take data in one step and you'd be analyzing that data in the second step and taking data at a higher frequency at that same second step. And then the third step, if your analysis pulled up any interesting candidates in the second step, you'd clear the queue and go back and immediately reobserve. And we would find many, many, many signals that were seen, and then when we went to reobserve, they were never seen again. And so we throw those away. Or we in doing the analysis, we'd see that that same signal had been detected on more than one telescope. So it's broadband, it's interference getting in the side lobes. So we throw that away. And I can send, well, it's a radio program, so it won't do any good. I was going to say I could send you a chart that shows of all of the years of Phoenix observing how many signals that we detected, how many were discarded because they failed one test or another, getting all the way down to there's nothing left.
Now, what does the process look like exactly? When you see a signal, do you have the infrastructure in place with these telescopes like the Allen Telescope Array? Do astronomers have the infrastructure in place to see that signal and know immediately? I mean, does an alarm go off when you see an interesting signal, or is it just discovered days later? And if you do discover it instantly, what's the process? Do you wag the telescope to see if the source is really localized to a single point in the sky before you tell other astronomers to look at this patch of sky? How does the process work there in modern context?
Yeah, I mean, the computer does all this, right? You're not sitting there. We used to be sitting there babysitting the screens, trying to do this and see whether we were finding interesting things. But now there's just a set protocol. And as I said, we do our observing at the SETI Institute in near real time. We don't just record data and look at it later. We do this in a stepwise process in near real time. So within 90 seconds, which is 3 stages of the pipeline, you know whether there's an interesting candidate there and one that you want to continue to observe. And that does not, I mean, it happens, but it doesn't happen all that often. And in that case, you go back and you just re-observe it. And you do, I think the number that we're now doing is 5 subsequent on-source and off-source observations of this interesting candidate from the target on the sky. And we require that the signal persists. And we keep seeing it when we go back on, and we don't see it when we point off. And that shows you that throughout the decades that we've been doing SETI, we have not actually had sensitivity to transient signals. And that's one of the things that can now change. It's changing first in the optical. There are a couple of new optical programs that are specifically designed to look for optical flashes, transients. And in time, we can do it with the radio part of the spectrum. So machine learning and the ability to have sensitivity to transients, I think, are what are shaping the future of signal analysis.
Now, the inability to properly study transient signals is really important because it hammers home the point that we've barely looked.
Yes.
You know, people always say that, oh, we've been doing SETI since the 1960s, Project Ozma. You know, we've been doing it for that long and we haven't seen anything. But we have barely even looked, is the truth of the matter. And we've just started. So how would you characterize that? You know, how much of the galaxy have we actually looked at with SETI?
Okay, so when SETI turned 50, I did this calculation and I said there are 9 different parameters that we're searching through to find an electromagnetic signal, assuming that an electromagnetic signal is what we should be looking for. And I put limits on how much you'd have to search in each parameter. And then I just multiplied all that together and said, okay, this is a 9-dimensional volume of search space that we need to explore. And I'm not good at imagining 9-dimensional volumes, so I said, okay, for an analogy, let's just say that the full 9-dimensional search space that volume is equal to the volume of all the Earth's oceans. And how much of the ocean have we explored? And when SETI was 50, the answer was 1 glass of the ocean. When SETI turned 60, Jason Wright and his students at Penn State redid that calculation. And at that point, it was up to like a small hot tub. So from a glass of water to a small hot tub in 10 years. And you can imagine that expanding. But you can see that the ocean is really vast. And there's a lot of work to be done here.
Now, the vast ocean, is the further away you have a star system, the less likely it is you could pick up a signal that's emanating from it. So is the focus on close stars right now?
Well, with our targeted searches that we've been doing, we have started close by and moved out, right? So we have a machine has to decide, okay, I finished on that star, what am I going to do next? And so we have a waiting mechanism for looking at the catalog, looking at what's above the horizon and how long is it going to be up there. And one of the strongest weights that brings a target up to the top of the list is its distance. Yes, we've been looking from close to far.
How about really close, as in inside the solar system? Now, John von Neumann had the idea that you could have a self-replicating probe and you could populate the galaxy within a few million years at sublight speeds, comfortably even, with robotic probes that station themselves in every star system in the Milky Way. And if you did that, you could have a very complete picture, a complete survey of the Milky Way. And if we had that ability, our scientists would certainly want to do that. So close artifacts of alien civilizations or close radio signals, do you look for those? And how does that differ from looking at a distant signal?
Okay, the answer is I couldn't find a Coke can filled with really advanced electronics in the solar system right now. So we haven't really explored the solar system. We started out by saying what's the minimum number of assumptions I can make, and so we started with point source moving on the sky at sidereal rate. That automatically excludes anything passing through our solar system. But there are other ways of detecting such objects. The infrared is one really good candidate. And so, again, Jason Wright and students at Penn State have looked at these satellites which have done 4-pi steradian mapping of the sky. And they've gone through and looked in the data. They've done archival data mining, looking for evidence of signals in there that don't correspond to a disk around a young star or another infrared source of emissions. And they come up with a few indications of potential targets, and people will, in fact, go looking at those if they haven't already. So it's a vast ocean, and we just need to continue to improve any tools that we have and pick up any new tools that might give us another way of looking. So I'm really excited about this new prospect for commensal observing on these gorgeous new 30-meter class telescopes.
What of James Webb? Does that offer anything?
It does, and there's certainly folks that are going to be looking at exoplanets, right? And so we'll very carefully watch those data. It's very unrealistic to think that we could ever get enough time on that general purpose telescope, which is being written to do, which has been built to do everybody's science, to be able to actually do a targeted SETI survey. But we can look at the data that it produces and see if we can do some data mining on these when they go looking for biosignatures around exoplanets and objects in the solar system.
The value of radio astronomy in SETI. If we start looking for things like Dyson spheres, if anyone ever builds anything like that, or if it's even possible, you're looking for an infrared signature from this thing. And that creates an ambiguity because you have protoplanetary disks and all kinds of things that emit infrared in the universe. So you may never be able to pick it out. But radio astronomy, that stands apart in that if you get a technological signal, it has a chance of being really unambiguous, right?
Yes, that's correct. And people have been thinking about the optical and the infrared and how you would distinguish a disk from a technosignature. For a while, people were looking at Boyajian star, this star that has huge dips in its luminosity, not the 1% that you'd get from a transiting planet, but 20%. And they wondered if that might be some indication of a megastructure or some other technology. In the end, as more data were taken across a wider range of frequencies, the community basically has decided that those drops in intensity are due to dust. But we're thinking along those lines anyway. And so in the radio, these frequency compressed signals are unambiguously, we think, technosignatures. But on the optical, if you found a monochromatic transient, right, that could be a laser. And that is going to be harder to explain as a natural phenomenon. It's getting to be a pretty interesting candidate for a technosignature.
Yeah, that would be very unambiguous because natural lasers and masers and things like that are very rare and they're characteristic in their own right. Yet if you see one that looks like something we would use in laser communications here on Earth, then nature's not going to do that, right?
Yes.
Now, there are people, and I'm a skeptic here, but there are people that say they're already here and that the UFO UAP phenomenon is evidence of the presence of an alien civilization. I suspect you have similar views on this to mine, but is that something worthwhile to look into, to figure out what are people seeing in the sky? And you yourself once saw something.
Yes, it's worth figuring out what it is, but I think there's no data that it has anything to do with extraterrestrial technology. Before, let's see, maybe it's only a couple of decades ago, high altitude pilots used to report lightning or something strange above these big thunderclouds, these anvil-shaped thunderclouds. And it took satellites with fast enough time resolution so that we could discover what we now call sprites and elves, which is essentially that lightning travels up as well as down. But for a while, they were really interesting, right? It's a UFO. And so it's worth trying to figure out what these things are because you might discover some new physics.
New atmospheric phenomenon that we were completely unaware of.
Mm-hmm. Yep.
Now, you yourself had a sighting that you resolved. Could you tell us that story?
Yeah, that was the most amazing cognitive dissonance. My husband and I were flying our plane from the observatory back to the Bay Area at night, and we were flying high, so we were under positive control. And suddenly we looked and saw this bright light at our 2:00 position. And it looked like the headlight of an oncoming airplane. So we called up the center and we said, what do you have at our 2:00 position? Because they hadn't informed us of any traffic. And they said, there's nothing there. And, my husband looks at me and I'm looking at him and we're looking and this light is really there. And, we're saying, this can't be happening to us. We're the big skeptics. And it went on for minutes until finally clouds that we did not know were there, very dark night, separated and allowed us to see the moon shining through a hole in the clouds. But for those moments before that resolved, it was the strangest feeling. So I know that people who see things really believe that they've seen things, and they're upset by them or disturbed by them or confused by them. And I know what that feels like. But in our case, we were able to resolve it.
Now, we also live in an age of drones that can do amazing things. It disturbs me when I see those drones, because to me, that's even more impressive than all of the accounts of UFOs. It's like, if I didn't know what that was, and I saw those drones doing their dance in the sky with lit up like that, I would be completely bewildered. And I wonder if the increase in UFO sightings is due to stuff like that, because we live in a very different world as far as everyone having access to lighted aerial drones.
Yes. And so the Olympic opening ceremonies will never be the same, right?
Oh, no. This is it's only going to get, this is the new fireworks, basically. Yes. Are these constellations of drones moving around, and they can even form in the shape of a UFO. And if you're looking at that in the dark, it may look like a solid object with lights on it. Mm-hmm. And it's getting muddier is basically what I'm saying, as far as trying to determine if there's something to it or not.
Right. Also, and our ability to program these swarms is getting so much better.
Yeah, it's scary almost. It's beautiful and scary at the same time, because that really tells you where we could go with artificial intelligence. And that's what we really don't need, is artificially intelligent drones coming after us and turning on us. Now, in regards to there's a question I want to ask you. It's no secret that Carl Sagan, whom you knew, based the character of Ellie Arroway on you. How did you feel about that? Were you like, Carl, that's not exactly what I want? Or did you embrace it?
Well, it's funny, because Carl wrote a book about a woman who does what I do. And I was back at Cornell at some meeting, and Carl said, come on up to the house. We're having a cocktail party tonight. So I went, and he and Annie took me aside, and they said, Carl's writing a science fiction book. And I said, yeah, I know. We all saw what kind of an advance he got in the New York Times last weekend, and we're all jealous as hell, right? And so Anne sort of chuckled, and she said, well, you may think you recognize someone in the book, but I think you'll like her, right? I let it go at that. And then when the book came out, Carl sent me a pre-publication copy that I read, and I'm going, wait, how did Carl know this? How does he know? It was really very, it just struck me as, that was me, but how did Carl know that about me? And the answer is that years before, I had gone to a conference sponsored by, I think it's the American Association of University Women, who brought into DC 70 newly minted female PhDs in the STEM professions. So I walked into a room full of 70 really bright women, and it just changed my life. I had never done that before. I had gotten so used to walking into a room full of men and being the only woman. Now walking into this room of fabulous women, it was really mind-altering. And so we sat there and did a little bit of amateur psychology, trying to ask ourselves, what was it that allowed us to get through this very leaky pipeline and succeed and come out the other end with a PhD? And there were a number of things that were striking about experiences that we had. First of all, one of the things, far in excess of statistical likeliness, was that our fathers had been the inspiration for our curiosity and our determination to do science or engineering. And our fathers had died young. In my case, I was 12 when my dad died. And we all learned this very important lesson in a very horrible way, which is the carpe diem lesson. Don't put off to tomorrow what you could do today, because tomorrow you might not have the opportunity to ask that question. And so at a very young age, we got good at this. Some of the other things, here was another peculiarity, which was that here we are, PhDs in STEM, and the great majority of us had either been cheerleaders or drum majorettes in high school. In my case, it was a drum majorette, because there were no title, it was before Title IX, and so there weren't any female sports teams that you could compete in. And we were all very competitive. And therefore, we competed at the only games that were around, which was trying out to be a cheerleader or a drum majorette. And we succeeded. So again, we were all very, very competitive. And a number of these traits end up showing up in the character that Carl built for Contact. And I remember I sent him a copy of that report quite a few years before we actually got around to writing the book. And so I think rather than being about me necessarily, it's the fact that I am very prototypical of women who succeed in entering male-dominated scientific professions.
As over the course of your career, has that gotten better? Meaning that is it a young girl listening to programs like this and gets inspired, goes and tries to become a scientist? Is it easier today than it used to be? Are we closing the gap in STEM?
Well, in some sense we are, and in some sense we haven't. I did a program at Cornell, I think it was last year or the year before, and I was astonished to find that whereas in my entering class of engineering at Cornell, I was the one woman out of 300 students, that year's class at Cornell engineering was 51% women, right? So we are breaking down some barriers. I have worked with a number of undergraduate women in a research experience for undergraduate summer program that we've had at the SETI Institute for a very long time. And I remember telling them that, in fact, it had gotten better, that the atmosphere and environment for young women in these predominantly male-dominated fields was getting a lot warmer and more inviting. And I talked to these women about this maybe a month before Jeff Marcy hit our screens. And I was so appalled that I actually called them back and told them, well, I guess I really didn't know what was going on. But wish them luck anyway.
Yeah,
So,
very, very disappointing situation. And I hear privately about the amount of sexual harassment and everything that goes on, but it's everywhere, in the movie industry and everything like that. And it's like, where was the professionalism? Now, to get back to alien life and ambiguity, we are in that situation on this planet in that we're not even sure that there's not a shadow biosphere, that Earth may have other forms of life that we just haven't seen on a microbial level that could be based on some other chirality or something like that. They could be a different hand, or it's hard to detect microbes and viruses and things like that. You need very specific techniques to do it. So given that ambiguity of life on Earth and that we just don't know, do you think that we could ever even recognize an alien civilization? Say they perceive time differently than we do, so their signals only come every 7 years or something like that. Does that keep you up at night, that we might not be able to actually recognize an alien civilization even if we saw it?
well, yes, that is a fact. And the only thing that I can say or do about that is to continue developing new tools. And eventually, perhaps, we can have something that allows us to look over a data record that is very long and recognize within it pattern that we miss in the moment. So I think that we just need to be building better tools to look at the cosmos in any way that we can. I mean, one of the best things about Alan Hill's 84001, right, when that controversy erupted with the claim that some of the structures in that meteorite, which had been collected in the Alan Hills region of Antarctica, so one of the best things that happened there was this explosion of new tools for examining micrograms of material, right? We just developed technique after technique of observing this very limited amount of specimen. And that served the field really, really well. So I hope that we will continue, because we're puzzled or curious about something, to develop new tools to look at the cosmos in different ways. And eventually say, oh, well, that's almost natural, but not really natural. One example that I like to give of that is pulsars. So rotating neutron stars, where their rotational axis and magnetic axis are not aligned. So we get this lighthouse beacon passing over us at a very particular period. And then what about a pulsar that changes its period abruptly? Well, we've actually seen that happen because of starquakes that change the distribution of mass in the system, and therefore the moment of inertia. But what we've never seen in our database is a pulsar that starts out with a period, changes its period to a second period, and that goes back to the first period. But that could be in our data, in our long-term data of doing pulsar timing measurements. And we ought to figure out a way to go looking for that with new tools. So,
now, do you anticipate, if you found a signal, do you anticipate that, say it's an intentional signal pointed at us specifically for the reason of contact? You know, this alien civilization looks at Earth and they're like, that has a biosphere and it must be one really nice biosphere, so there may be intelligent life there. So we're going to send a continuous signal towards them, and you pick it up. Do we have any hope of decoding a message, or are we simply going to stumble across some alien's radar?
Yeah, well, the message, the important message, is the answer to the "Are we alone?" question, which is no. In terms of, are they going to tell us how to build a better supercomputer or how to live to be 200 years old? I don't know. And there are other experts in the world who have decryption skills that I certainly don't have. And the thing that you might consider is, if this is deliberately sent, they might put effort into making it anti-cryptographic. That is easy to interpret, or at least easy in terms of their frame of reference. So there might be some hope of actually understanding a message because they want it to be understood. Otherwise, they wouldn't have bothered to send it.
Now, METI, messaging extraterrestrial intelligence. So you pick up a signal. Should we respond? What's your opinion on that?
My opinion is that we're too young as a species and as a technology. So if you're going to transmit a message back and your transmitter's on for 5 minutes, well, that message, returning message, is going to go past the civilization you're sending it to in 5 minutes and be gone. And they'd have to be looking at us at just the right time and just the right way to see that we said, yeah, hello, back. And I think the chances of that are pretty small, and transmitting is costly. Therefore, my contention is transmission doesn't make any sense until we can do 10,000-year projects, right? And just turn the transmitter on and keep it on. Now, that's the way I feel today. If we actually got a message and there was some ability to interpret it and it invited a reply, then I would have a different answer to your question. But just arbitrarily transmitting, as the METI people would advocate, because we want to get their attention and have them then concentrate on us. As I said, I don't think we can do a good enough job at it because your transmission has to be long-term, and we're not yet long-term.
The future of SETI. So we live in a world where you have Yuri Milners that will put money, they'll make their money in business and then put it into SETI searches and things like that. So if someone came up and said, Jill Tarter, here is $1 billion, what would you do? What SETI experiments would you do on that scale?
Well, I would assume that the $1 billion was going to be spread out over a significant amount of time, because there just isn't $1 billion worth engineering and technology that we could do today that would enhance the search greatly. There are incremental improvements, and I'd love to have those funded, but a big, here's a cure for cancer kind of campaign, big chunk of $1 billion, I put it into an endowment so that you could live off the return on that endowment into the future. So it would be a good way to fund what is likely to be a multi-generational program, right? And it would be enormously wonderful to have such an endowment, because not only do you have the problem of dealing with the best and the brightest of the young engineers and scientists and say, come work with us. And you have the problem of, well, you might not succeed in your working lifetime, and that might not be something that you can live with personality-wise. But you also then wouldn't have the problem of trying to convince them to become part of this program, and also then having to say, I'm not sure I can make payroll at the end of the month. So an endowment for training our successors and keeping this work alive over multi-generations, I think would be wonderful. So that's what I do with the $1 billion.
Now, my last question for you is, okay, Seth Shostak thinks that we're going to find it within 20 years, and he's bet the world a cup of coffee over it. Yep. Would you bet the cup of coffee?
Rather than betting on it, I'd rather build a new instrument to look in some other way. Right? I'd rather just do the work of trying to get better at the job, because I don't think that Seth knows, or I know, or anyone knows, and we won't know until we succeed, what the answer to the "are we alone" question is. So let's not bet. Let's just explore.
The first SETI message we get is, I want my cup of coffee. Seth.
Okay. All right.
All right, Dr. Tarter, we are out of time. Thank you for joining us today, and I hope we can do this again sometime.
Okay, John. Thank you very much.
Thanks for listening. I am futurist and science fiction
John,
author.
Wrong channel.
No, it's not. Thanks for listening. I am futurist and science fiction author John Michael Gaudier, currently hosting Event Horizon and wondering where Anna actually came from. One day I had a tablet computer, the next I had a boss. Very disturbing. Be sure.
And that's enough of that.
YouTuber forever. Like, subscribe, and hit the bell.